In this video, we're going to be discussing Gibbs free energy in more detail. And to go into that, we're going to be discussing some properties of it and how it relies on different variables. So we're going to start off figuring out what the differential for Gibbs free energy is, just like we did in the last video when we used the differential of internal energy to find Maxwell's relations. We're going to do the same thing, except for we're not going to take it one step further and go to Maxwell's relations, but instead talk about the partial derivatives and what they really mean. And then we're going to cover a couple of last topics based on Gibbs free energy that wrap up the end of chapter 3. Okay, so this is all about the properties of Gibbs free energy. Okay, so we know that the definition of the Gibbs free energy, G, is equal to the enthalpy minus temperature times entropy. Now these are all for the system. Now if we want to talk about infinitely small changes in G, we can write this as dH minus d of the product Ts. If I use the chain rule, what I can say is dH is subtracted by dt times S, or I might write that as S dt, and also subtract off our TDS. Now, what we're going to do is subsequently plug in our DH term based on our enthalpy. So, we know that, I'll start here, our enthalpy is equal to our internal energy plus PV. If we look at infinitesimally small changes in our enthalpy, this is equal to du plus d times the product, or the d of the product, P times V, pressure and volume. Factoring, or using the chain rule, I should say, for that, we get that our infinitesimally small changes in enthalpy is equal to infinitesimally small changes in our internal energy plus P dV plus V dP. Okay, so ultimately we're going to plug this into here. And so what we get is dG is now equal to du plus PdV plus VdP, so VdP, minus SdT minus TdS. Okay. See, we still have an expression here for our internal energy. Now we can write that in terms of our fundamental equation. So we just discussed that. The du is equal to our S dt. I want to make sure I'm writing that out correctly. It was, sorry, not SDT, but TDS minus PdV. So now I'm going to plug this in for our du. And so what I might get out is some d values here, some infinitesimally small changes that cancel each other out. So plugging this in here, I have dg is equal to TdS minus P dV plus P dV plus VdP minus SdT minus TdS. It's a lot. But we see it, we have things that cancel. So in the end, dG is equal to V dP minus S dt. Now, just like in the case for internal energy, we're going to figure out what the differential is for this. So what we see is that our Gibbs free energy here can be discussed as a function of pressure and temperature. Clearly, it depends on those two variables. So if we look at the differential here, we have that our differential states that dG is equal to the partial derivative of my Gibbs free energy in terms of, well, I just pick one of my variables, I'll say pressure first. I'm going to take the partial derivative in terms of pressure at constant temperature and multiply this by dP. And this is going to be plus my other partial derivative. So d, my partial in terms of G, and my in terms of my temperature at constant pressure dt. Okay, so based on that, what that would tell me is that my volume is equal to my partial derivative of my Gibbs free energy in terms of pressure, and my entropy, my negative entropy, is equal to the partial derivative of Gibbs free energy in terms of temperature at constant volume. So I'm going to write that out up here. So I'm going to start with my relationship with the Gibbs free energy and pressure. So thus, my partial derivative of my Gibbs free energy in terms of pressure at constant temperature is equal to volume. And my partial derivative in terms of my temperature at constant pressure is equal to negative entropy. So qualitatively, what does this mean? So I'm actually going to start with this second one here. So fundamentally, we know this partial derivative is saying that how does Gibbs free energy change with changes in temperature? Gives us an idea of the slope, right? Well, we know that our entropy is always positive. This is just regular entropy. Now entropy changes. This is always positive. Okay? Unless you're at your absolute zero, then it's possibly for a perfect crystal equal to zero. But we're saying that it's always positive here. That means that our Gibbs free energy is always decreasing with increasing temperature. Okay? So as we increase our temperature, our Gibbs free energy is always decreasing. Also, S here is kind of the magnitude of our slope. So S really kind of gives us information about how this slope changes, how quickly it changes. So as our entropy increases, our Gibbs free energy decreases more quickly. Okay? The slope is more negative, so it's still a function of temperature. It's just more sensitive to it. So I'll say with increasing temperature. So what we can say is that as S increases, our Gibbs free energy becomes more sensitive, more temperature sensitive. Okay. So this is actually pretty interesting, figuring out based on this partial derivative. Now what does the other one tell us? Well, I'll go over here, we don't need this anymore, and we'll discuss the second partial derivative. So now instead I'm going to be looking at my partial derivative of my Gibbs free energy in terms of my pressure at constant temperature, and this is equal to the volume. Okay? So we know that volume is always positive. You can't have a negative volume. So what that means is that our Gibbs free energy is always increasing with increasing pressure. Okay, so my slope is always positive, and so it means that my delta G, or my Gibbs free energy, increases with changes in my pressure here, or increasing pressure. Now, the magnitude of the slope is dictated by my volume. So as volume increases, my Gibbs free energy increases more quickly with increasing pressure. That is to say that as volume increases, my Gibbs free energy becomes more sensitive to pressure. So as my volume gets larger, I have larger and larger volumes, my Gibbs free energy is more sensitive to pressure. Okay. Now, this is kind of some really interesting relationships here. You could have used what we did up to this point here to find Maxwell's relations for Gibbs free energy, but that's something that's really, at this point, not what we're really focusing on. We're going to sit and focus on how Gibbs free energy changes, because in the end, that's going to tell us how our system is changing in terms of its spontaneity. Okay. Finally, we're going to go on and talk a little bit more about our Gibbs free energy and pressure. So we're going to continue on with this. So this is more on Gibbs free energy versus pressure. So right now our differential here, we have dG is equal to VdP minus SdT. If the system is isothermal, so what just happened is that someone came into the classroom, the security guard. So I edited that part out, so we're going to there's going to be a break in what was recorded. So you can never plan for these types of things. So going back, we're talking about more about our Gibbs free energy versus pressure. dG is equal to VdP minus SdT. And what I was getting at was that if the system's isothermal, that dG is only equal to VdP. Now, if we want to talk about total changes in Gibbs free energy, what we can do is we can take an integral of VdP from pressure 1 to pressure 2. Now, this in itself is kind of vague. So what we're going to do is, instead of talking about just volume and Gibbs free energy, we're going to talk about molar volume and molar Gibbs free energy. All that means is we're dividing by the number of moles. Okay, so your measurement is no longer extensive, it's intensive. Okay, and so what we're going to say is, or delta GM is equal to the integral from P1 to P2 of Vm dP. So this is the molar volume. Now we're going to break this up, this equation here, and solve it for two different systems. One would be solids and liquids, and the other would be gas. So for solids and liquids, our molar volume does not change significantly. So we could figure this out using our isothermal compressibility. If you recall, we talked about that earlier on, a couple chapters ago. But it's safe to say, you change the pressure, you're not going to change the volume of a solid or liquid significantly. So if that's the case, that means that Vm is not dependent on pressure. It's a constant. So what we can write out is our change in our Gibbs free energy, molar Gibbs free energy, is equal to Vm integral from P1 to P2 of dP, for my change in molar Gibbs free energy is equal to my molar volume times delta P. Now, if we're talking about gas, go up here. So for gases, now our molar volume is dependent on pressure. Our volume will change significantly if we change the pressure. And so we can write our molar Gibbs free energy change as my integral from P1 to P2, my molar volume dP. Now we can't pull this out anymore. What we can do is we can say that the molar volume is going to be equal to RT over P. So this is going to be equal to my RT times the integral from P2, from P1 to P2 of 1 over P dP. And so my change in molar Gibbs free energy is equal to RT times the natural log of P2 over P1. Okay. So we see that there is a difference here depending on if we're talking a solid or a liquid. The last thing I want to bring up is the idea of fugacity. So this would be, it's kind of a non sequitur in terms of this chapter, but something that I think it's good for people to know. So fugacity is basically correcting for the idea of a real gas. So real gases do not behave with the same pressure as ideal gases. What it is to say is that you have interactions with real gases, and so maybe your pressure is less than it would be ideally, or more than it would be ideally. And so that's the idea of fugacity. So we write out fugacity as this fancy F, which is equal to the fugacity coefficient times pressure. Now, for those of you who've taken analytical chemistry, this is analogous to the idea of an activity coefficient, and concentration. So rather than ion screening, what we're having here is molecular interactions. So this is our fugacity. And this is our fugacity coefficient. So what does that mean? It means that we can correct our pressure based on how gases really behave. So if we have a fugacity coefficient that's less than 1, that means that our molecules are sticky. That means that they're attracted to one another and they don't have this full pressure that they should have. If our fugacity coefficient is greater than 1, the molecules are repelling each other. I'm going to say strongly repelling each other, because they're always repelling each other. But what this means is that repulsion is dominating. Okay. This concludes what we're going to really discuss with chapter 3. There might be more that we want to discuss about it, or reiterating things, but I think that this is really the lecture material that we want to cover. So thank you for watching.